What's the hydroxyl value above the line? You can just kind of explain how we get there. This is the hardest question I've given, so take a moment.
You essentially multiple of 6.
So you have 6 hydroxyls. That'd be kind of what would be on the bottom line of the calculation, right? So you'd have, if we said, what's the hydroxyl value? It would be the total mass of everything, right? Divided by 6. And then that divided by 56,100 would actually give you a hydroxyl value, right? But you see, it's a number. I don't know what that number is. I expect you to be able to figure that out. You need to know the process. You'll see why this is important in just a second. Now let's switch to below the line. How many free hydroxyl groups are there below this line?
Do I count the LIOH?
No.
Is that the line?
Leave that one out.
Okay. 4.
4 here.
Oh, plus 2, 6.
So there were 6 above and there's 6 below. How many esters are there below the line?
3.
3. How many were above?
3.
3.
How many free acid groups are there below the line?
None.
Okay. How much mass did we gain or lose moving from top to bottom? Theoretically, none. This reaction turns out to be quite an interesting one in that short of NMR, and it needs to be high resolution NMR, because they need to be able to tell the difference between that CH2 and that CH2 very definitively, which with a low resolution NMR you can't. With our 500 and 600 you can't. This would be distinctly different than that in carbon terms. Turns out to be problematic with regards to how do you determine the extent and progress of the reaction. We run into these things that seem, it's easy enough to draw this. This is our goal. We have to make all of our monomers into AA monomers, and they're different types, but they're both AA monomers. We have to get to that to have usable material. Matter of fact, if we just dump this in with the rest of what I'm going to show on the next page and try to run it all at once, we would get a gelled piece of junk that was useless. So we have to do this step first. How do we tell progress? Here to here. IR will not be definitive. IR will tell you that you have the same range of hydroxyls as you have before and after. It'll tell you they have the same range of esters, but it won't define that that ester is any different than that ester.
What gamma molecular weight will be different?
Well, you're going from what should be about 878 plus whatever that is, and now you've rearranged it to be across different molecules. Your molecular weight average is changing slightly, but you got to keep in mind, from top to bottom, it's not changing. Because this is high molecular weight and this is low, and now this is higher and this is lower, right? So your average is about the same. So it's not molecular weight. Now GPC won't resolve this difference, because this is all you got, right? If you had a bunch of special low molecular weight columns, you might. Maldi might. Maldi would do it.
Now your 2 chains are on 2 separate molecules as opposed to both chains being on one. That
Right.
is the biggest difference here.
So you would have a difference in GPC would be here, right? That and that would be distinctly different. And this would disappear if this happened, and then these two would overlap. So there'd be, instead of being bimodal, it should be wider, but unimodal.
But wouldn't the center of your peak change? Because, I mean, the triglyceride will travel through the column faster than the lithium one.
You'd have to, again, it'd come back to how you packed your columns and what columns you picked as to whether or not you could refine that separation. You know, if this were 80,000 molecular weight and that were 100, yeah, you'd see the amalgam in the middle at 12,000 or whatever. But being 878 and I think 136. Those aren't that far apart anyway on GBC when you focus on high molecular weight. So let me cut to the chase. There's not a lot of ways to do it. You can't do it by hydroxylate titration. You can't do it by acid value titration. You can't do it by saponification. You can't saponify any of this. Turns out, though, that this is not soluble in methanol. So you can use solubility parameter to determine when you have a good endpoint. But again, the family had to develop this. It took time. They had to figure out the right blend and the right temperature so that this was not soluble in what they checked it in. And then as the reaction proceeded, they would put it in and they would shake it and they would look for optical clarity. If it was optically clear, then everything was in solution. They were at a finish point that was sufficient to move forward. Now it seems crazy that with the billions of dollars of equipment that you could buy to measure things, that this comes down to a solubility check. And I like this example because it's going to happen to each of you at some point in your careers. You're going to have lots of wonderful equipment available. And you're going to have to step back and go, now wait a minute. This should be simple, but it's not. Right? This should be solvable, but it doesn't seem to be today, at the way I'm looking at it. And then you're going to have some undergraduate go, hey, why don't you just do a solubility check? Right? And it's either you're hired or you're fired, depending on how you feel about that undergrad. Real simple. So we produce this in the first stage. We drive that. And lithium hydroxide is actually a good transesterification catalyst. That's why we're using that. And then we go to this stage where we put those molecules in, and we add this monoacid. That monoacid is compatible with those monoglycerides as well. And when we blend those together, now we've put a chain stopper in here. These are difunctional. This is monofunctional. They can react, and we want some of them to. But now we want to dump in high functionality materials. And penterithrotol is notorious for creating gel. So you have to have this monofunctional for two reasons. One, to prevent this from being so branched that it causes a loop back, closes the loop, and becomes a non-flowable, non-soluble product that we would call gel. Right? It's practical gel. This is also trifunctional, the trimolytic anhydride. But this is also added for another reason, and that is to get greater than 75% oil links, you've got to add additional fatty acids to get there. You'd be right at, I think you'd be at 71 if I did the rough math right on the first page with the charge, and you left out this fatty acid. Now, since I haven't given you the building block lecture on alkyd building blocks and oils, you can write this out real simplistic. It's a C18 chain, and it's a diene. Usually we do the nomenclature that's common. The simple nomenclature would be this: C18, 2, and then you need to know that it's 9-12 substitution. So we count from this end. And most of the fatty acids we use for alkyds are C18, but not all. If someone uses coconut oil, then there's a lot of C8, C10, C12. But animals and plants are different. Plants tend to have even numbers in their fatty acids. Actually, animals do as well, except porpoise. Porpoise is one of those that's like C15, C17, C19. And if you look, I don't have a chart of it. Let's see if I can draw this real quick. This is kind of, these are cool, these are Tea Party points. These are things I use when I'm at that Tea Party. If you look at carbon atoms, and this happens in all of polymer science, so cement this, it's real important. You look at carbon atoms and you look at Tm. If you go from 1, well, I need to start a little higher than that. Let me start at like 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 18. And there are some that are above 18, but most plant matter that we would use would be at 18. Let's see, the TM would be something like this. And what you end up with is the odd ones form a line here, and the even ones form a line here. And it has to do with if you make a 3D model with some bead and stick model, and you lay them out, and you can make 2 or 3 of them and try to lay them together, they pack differently. The actual chain length causes them to pack differently. And you'll see this in nylons. You see, we'll talk about it again then, because if you do a nylon 3 or a nylon 5, they don't have the same crystalline capabilities as nylon 2, which is peptides, or nylon 4 or 6 or 10, which we make all the above. 6-8, 6-6, 6-10, 10-12. We tend to use the even ones. That's based, again, on raw material sources. So this is real important. It's a zigzag if you draw it properly. It's a little odd. And Lon Mathias did a real good job of this throughout his career, where he actually spent time trying to understand why they pack differently in nylon systems using solid state NMR. So he did a lot of work on that, specialty nylons that he made. All right, zoom back here. C18, semicolon or colon 2, and they're at the 9-12 position, which means they're non-conjugated. And I'll bring back the importance of that as we wrap this up Friday. So we had pentothal, acetic acid, trimethylene hydride, and I recommend that y'all take the time and look at those charge numbers. Y'all have these charge numbers? You didn't write them down, so I need to send it to you, right? Let's do this as homework. If I can turn it on here. For sake of brevity, I can send it to Stephen. One, he can share, or he can show real character flaws. Let's see. That would work. There we go. You'll want to just get a column out here and do molar. Okay? You will need one more number to do that. And that number is later in the presentation, so let me grab that as well. I got a lot to cover in one more lecture. Let me give you, there's linseed, that right there, okay? So you have the composition. Because to get an average molecular weight, you've got to have the average fatty acid composition, okay? Which means you need one more. We'll do that. That should give you plenty to do this. Yeah, so there's oleic. It's also C18, but it's only one. Linoleic, which is 912, and linolenic, which is 912-15. So none of them are conjugated. These are all the fatty acids, the main ones that are in linseed oil. And you'll see that from the slide. Just calculate moles, okay? In order to do that, you have to do molecular weight, and then you have to divide by the charge amount, right? So you get moles, because I want you to end up with a molar ratio. All right, back to making something. So here we are, we put all this together, and we slowly heat it, slowly meaning probably in the case of somewhere between 6 and 12 hours, we heat it to 238C, all of this together, and we end up with a structure that looks something like this in the finished form. So this is a pretty neat finished form. And you see where here's the pentoerythritol, the tetrafunctional alcohol residue. Here's the the isophthalic acid. Here's the fatty acids all over the page, right, giving you the acid or the oil length. And then, of course, here's TMP. Here's glycerol. Here's a little bit. I don't know if you caught it on the one slide. It actually says we want about 10% excess hydroxyls. And you want that. It's another method of keeping it from gelling. It also turns out that when you make polyesters for a lot of applications, including industrial plastics, if you have free hydroxyl groups, you will better disperse colorants and pigments. It's a very simple thing, but it turns out to be absolutely critical. And most people don't buy just chunks of polymer with no color and no additive and no filler. And if you can't disperse it properly, then you get something that has what we call bleed or color drift or color. It'll have speckles and spots. So you have to get pigments, fillers, things like that evenly dispersed. And just leaving a few hydroxyl groups in each molecule will help to facilitate that. It's a polar entity that's good at disrupting pigment agglomeration and things like that. So this is kind of what the structure would look like. This is what you'd buy in the can if you went to Lowe's and said, I want a very long oil alkyd wood finish. There wouldn't be any pigments. And then you would take this and you'd rub it out onto, and it might be diluted with some solvent depending on the viscosity range that you wanted. And you might buy it without solvent and then dilute it so that you get thin films when you wipe it on. Now, if we took a little bit of the colored bodies from the bottom of the petroleum refining process, that's most often called pitch or bitumen, that last part that we make asphalt from, if you took a little bit of that and you sprinkled into this alkyd, you'd make a stain. That's how we get a lot of the colors to make, whether it be a red oak or it be a walnut. I'm just giving you a little feel for how we utilize the material. This would be cast as a film. It was an excellent film former. It would form smooth, thin films, even at 100% solids, because of the low viscosity and low molecular weight. And then it would auto-oxidize without any other catalyst. It would take it probably 24 hours before it was tack-free. It'd be sticky at first, and it would become tack-free. It's a usable product as finished for certain applications. And in the main, this would be used for wood coatings, where these aromatic groups would add a slight amount of color, a little bit of a yellowness. But when you do wood coatings, it's okay, unless you have some sort of bleached wood, to have a little bit of yellowness, because the grain is actually accentuated differentially that way. I don't know if you've ever seen a cedar, clear-coated piece of cedar, but it really brings out the differential between the redness and the whiteness of all the different grain boundaries. So that's an aesthetic thing. It turns out oils like this like cellulose. It also likes lignin. So it's a product that is used naturally to do that. And we can't replicate this with strictly petroleum products and get that kind of finish on wood surfaces.
So when you have to use solvents for these can't be water soluble. So I mean, you're talking like for commercial coatings, like you can't make latexes out of this and stuff, and like all coatings are going to water-based latexes now ultimately.
All that can are. You're correct. But we have a problem when we coat wood. I'm going to correct you on a couple of things. This could be sold as 100% solids, no solvent. A lot of people would dilute it because they wouldn't want it to be that thick when they put it on their substrate. That's different. But it could be sold as 100% solids. So we would feel okay saying we sell a 100% solids product and there's no pollution. You have to then dilute it with something that meets your needs. That's not uncommon for all paint. It's not uncommon for lots of products, including composite resins and things like that. You have to figure out how to process it. Everything that can go to water-based is in the world of surface coatings, in the world of all of these types of materials, adhesives, sealants, caulks, everything that can be. But we have a problem. How many of you have just taken a piece of fresh cut wood or dried wood, either one, and you wet it with water and watch what happens. The water will, and I cut cedar with my son this weekend. We cut some slices of cedar so that he could take it to his class and they could count the growth rings and everything. And I said, you want to see it really stand out? And I just hit it with the water hose. And boom, it looks like it's got a glossy clear coat on it. And then it wipe all the dust off and it really brings it out. The problem is the water gets absorbed in. You know how you have rings, and in a wood substrate, rings indicate densification, right? If you, a given part of the tree would start to grow in spring when the weather's good, it's growing, it's growing, it's growing, and it gets cold, and then the density of the rings change. And then its growth slows down, and they get more dense, and then it stops growing, and then it starts regrowing. That's this kind of compaction and compression. So there's a differential in density, which makes for a differential in uptake of water, which makes for a substrate, if we're coating it and we use water, we're getting swelling that's differential in X, Y, and Z, but also in these ring structures. It's very hard to coat wood with water-based products. Because as soon as you add the water, it swells. Then the coating, it goes through the process of going from a liquid to a glass, or a liquid to a non-tacky material. It might not quite be glassy, it could be leathery. But the coating is losing mobility as the rings are shrinking back down and water is being involved. So as of right now, everybody that does use water-based only uses it after they have sealed the wood in the main. People try it all the time. Don't get me wrong. We've tried it as well. We've taken oil-modified latexes and cast onto wood, and we still have the same problem. And part of the problem is that the water makes a boundary layer, and it won't let the coating absorb into the grains. So you get the same aesthetic appearance. But if you smack it with something, it delaminates because it wasn't absorbed in, because all of the cellulose that would normally orient with this and start to actually be swollen and penetrated and reacted with, all of the cellulose is tied up hydrogen bonding with water when you use that. Stephen, would you mind running to my office and grabbing that gun stock? I hadn't brought that in here before, I haven't.
No.
Everybody okay if we play with the gun stock in the classroom?
Absolutely. Because, yeah, regulations on, like, primers and stains are different than on coatings.
Absolutely, and they're all different,
Yeah.
and they're drastically different between if you and I as an industry, like Ethan Allen, are coating 1 billion pieces of furniture a month, versus you finding one fine piece of furniture from your father's home and wanting to restore it. You can use as much solvent as you want. No one regulates it. So it's drastically different. Now, there's another chemical problem with what you said. And when we made our oil-based latexes, we run into this all the time. Let me back up one slide. And this is something I want you all to be very tuned into in all of the chemistries we study together. We catalyze this with this. Okay? It's basic in nature. But we know that polyesterification can be catalyzed by acids or bases. And we actually, if we look at all the mechanistic slides that I had, it's metal acetates and metal oxides, and there's lots of combinations depending on what temperature range we use. But now we have to remember the arrows. The arrows go both ways. So what you don't find on the shelf anywhere really in the world is you can't get a polyester of any type that is made in water that sits in water on the shelf. Because what you will measure over time is an increase in acid value over time. Month over month, the acid value will go up, and as that's happening, what we're doing is we're cleaving these esters. We're hydrolyzing. There's plenty of water there. Now the rate is slowed if we have a stable dispersion, because in the particle it's a hydrophobic environment. But external to the particle, and in order to stabilize the particle, we have to have polar groups on the surface of it, because we're trying to stabilize it in water. And we'll touch on this again when we get to emulsion versus dispersion versus bulk and solution, the process section of the class. So what we would do is we would increase, if we knew you were going to use this, and we knew you wanted, and we were designing this for you, and we knew that what you wanted to dilute with was not toluene and xylene. You wanted to dilute with water. We would increase the number of hydroxyl groups. so that this was thinnable. We would call it water thinnable. We would still sell it in a can at 100% solids, but we would write on the can that before application, we recommend you thin. And this material is designed to be water thinnable. Now, water wouldn't actually be a solvent then. Water would be a diluent, and it would blend in, but only at certain ratios. And if we put too many hydroxyl groups and too many carboxylic acid groups, even if we thinned it with water, when the film dried, it would be water sensitive. There's a balance. There's a balance of properties. What do we make in a can that you can use that still meets the need in the end? This is an interesting thing because this is a laminate, and the laminate it's a well-made. I can't remember I used to know the company's name that we did the work for, but it's a well-made. This is for Remington 700 for those of you that do have rifles, and it's chipped. Otherwise, it would be on one. Okay, but it's a good example. So what I want you to do is look down inside here. What we did is we took this stock and we put it into a pipe. And we filled the level of liquid above that, and then we pulled a vacuum for days. It took days the first time we did it. It pulls all the air out, and when it pulls the air out, there's a porosity that needs to be filled in because it's below the liquid level. The liquid keeps seeping in. It's the low viscosity liquid. It seeps in. So we actually, for lack of a better word, impregnated this with resin. And you can see where when we heated it, that resin kind of blows back out. But this resin is an alkyd, but an alkyd modified phenolic. Phenolic would be aromatic OH with some growth pattern. We'll get to that structure in 3 weeks. We'll be making phenolics. But the alkyd part loves the cellulose part of the wood. The phenolic loves the lignin part of the wood. Those are the two main compositional things. So this has, I think it's 7 times the break strength in flex this way, I think. I think it's 5 times in flex this way, which is good. But most importantly, what this has is once that resin goes in and cures and seals, this doesn't have distortion when it's wet and dry. So you don't change the accuracy of the weapon. And this would be no different for the musicians in the room if you made a guitar neck. And the guitar neck were wooden, right? If it's wooden, then every time the moisture changes, you really need to retune it, right? But if you made it carbon fiber, and it had a coefficient of thermal expansion of, 1 part per billion, and it had no sensitivity to moisture, then you might make a guitar that didn't need to be tuned until the strings broke. And conceptually, people work on this. Now, they don't have the same acoustics. Carbon fiber just doesn't hum like wood. We're not used to hearing that. But if you look at this is an example where something like this was modified even further to be more aromatic. It seals this, and then this has no distortion, really, no detectable distortion under 50% to 100% relative humidity day in and day out. Kind of a cool use of polymers with the natural polymer that's there, which is the wood. Yes?
You said that it turns from tacky to glassy layer.
Yes.
So, is it because of the oxidation?
Auto-oxidation,
How
yes.
does that happen?
And I'll need to cover that.
Story
Auto-oxidation.
does that too.
What's that?
Story does that in his class.
Yeah. Does he do it in 7.0?
703.
Does he? Okay, so you'll get to touch on it again. Auto-oxidation is basically where these, let me back up a step. I have the slides in these notes. I'm not going to jump forward to it right now. This turns out to be really, really abstractable. You're getting pi conjugation across this double bond and this double bond, so that ends up being abstractable. In the presence of oxygen, you'll form radicals by abstraction, and you'll form radicals in the form of hydroperoxides. That initial stage is called primary autooxidation, and it takes up oxygen, but it doesn't lose double bonds. There's some important parts to that in the process, in the mechanistic part of it. And then that ultimately, those peroxides would dissociate to then form ether linkages, where you get CO radical plus a C radical, and you form ether linkages. Ultimately, when you were starved of oxygen because you had vitrified, you would get C radicals that would combine, and you'd make methyl bridges or methylene bridges. Okay? But that's the autooxidation process. All right. That was an example of a very long oil. This is an example of a long oil, and I'm going to move through it a little faster. Mainly used as topside marine coatings, and I'll say that used extensively in topside marine coatings when it's a wood substrate, and which a lot of sailboats still are, a lot of small structures still are, even though the hulls might be commonly fiberglass and those kind of materials. So these are also used as architectural and maintenance as brushing enamels, and that's what this is right here. This ugly gray that we have all over the building, I don't know who thought of this. That is an alkyd. Because when they get painted on, you can smell solvents for about 30 days. It's an alkyd. And I'm sure it's a long maintenance enamel. As we move to less oil, we can use a wider variety of oil starting sources. And since I haven't covered oil yet, that makes this conversation a little more awkward. But I do want to say tall oil. Not everybody knows what the tall plant is, but it should be obvious once I say it, it's obvious. Tall oil is the vegetable oil product that comes from pine trees. That's why they call it tall oil. It's the tall plant. It's goofy. But this Hercules plant on 7th Street, they built that plant to produce tall oil. And there's lots of other products from pine, including some cellulosics like nitrocellulosics and things like that. But that Hercules plant used to be a supplier for munitions and other raw materials for the whole company. But they also made tall oil-based alkyds that went to the coast and supplied the shipping industry, the shipbuilding industry down there. So you can see how this works. Now Hercules just has a skeleton crew there and they don't do much of anything. Hercules used to be part of DuPont. You need to know that as well. DuPont was the original maker of most gunpowder, trinitrocellulose or trinitrotoluene nitrocellulose, those kind of combinations. But a lot of those early materials came from pine trees. So these are slower to dry, but we have an advantage. We're now going to increase the molecular weight. And as we increase the molecular weight, we're moving up, so it's more and more of a solid to begin with. And by dry, I mean it becomes a tack-free surface. This is the kind of formulation we would start with for long oil, linseed oil, linolenic acid, phthalic anhydride, pentorithiol, and we just use an ethanolic KOH. This is kind of neat. This is real simple. Heat oil, fatty acid, and pentorithiol for 75 minutes at 250 C. At the end of that period, you'd add the phthalic anhydride and hold for 240 for 8 hours. That's the cook instruction. Pretty simple. What are you laughing at? It's just kind of...
Sounds like a cookie recipe.
It is. It's just like that. You have 60 to 75% weight in oil, and you get 10 to 15% excess hydroxyls, and that keeps us from achieving a gel point. But it also gives us, with that beginning with the end in mind concept, it gives us some chemical handles that we could react with if we wanted to do something else, such as an isocyanate or a melamine cure. But it also gives us hydroxyls to help disperse pigments and bond to substrates and give better adhesion. So in sealants, adhesives, coatings, even in composites, these kinds of functional groups tend to help wet fibers and hold those fibers more intimately. And if they're held more intimately, there tends to be less interfacial region, so they don't have the same reasons for failure. I hope I'm doing an okay job of tying together some of the chemistry with how we use them and why. I jumped through that real quick, but you'll have a very long oil to do some calculations on. This is medium oil. Kind of the discussion of this is similar. Very often, medium oils are very versatile, because we've got about 50% balance of petroleum derivatives and a 50% balance of vegetable oil derivatives. So we've got more latitude in how we design it, and it becomes more linear. So we start to increase the molecular weight and have more of the traditional polymeric materials type properties. Structure would be something like this. In this case, it really does start to sound like a drink recipe now. Add some linseed oil, a little glycerol, a couple of limes. That's not really lime. Phthalic anhydride and some more glycerol, and you do this in 2 doses because this is a staging process, right? So you heat the linseed oil and glycerol, 425F, and I went back and forth on purpose. I leave it in F in some, I leave it in C in the others, and that's because most people that cook resins still are old school. Most people that produce polymers in the U.S. are still old school. They use Fahrenheit for everything. It drives me nuts, and I have to do conversions every time I'm with them. It drives them nuts. But so then you add your limes and continue heating for 30 minutes. Add phthalic anhydride slowly, and then add glycerol and maintain 450 until acid value of 6 to 10 is reached. Look at that, 6 to 10, 6 to 10 out. Pretty straightforward. But what you end up here is you have a higher, if you look at the ratio, you've got a lot more aromatic content here, and you're making much more linear system. And now you're starting to leave acid groups and hydroxyl groups. And that's to keep you from having a P-gel situation. So let me pause there. Yeah, we really need to meet on Tuesday. Because then we could do the rest of polyesters. We'll try to finish the overview part of it on Friday, finish the details on Monday, and finish the calculations on Tuesday. And then we'd be ready to start polyamides or urethanes, whichever one's ready next. Wednesday. Yeah, we could do that. Okay. I'll try not to use their chat. It's hard for me. Sorry about that. And I'm not even a talker. That's what's funny. I'm so excited about sharing information with y'all that I think will be valuable in the future. But I can't stop. But I need to share a small subset. All right, get out of here. Thank y'all. You want to hit send and receive, you'll have that. You share it with your colleagues. I have all the email addresses, but I'm going to probably...
So are they doing that tomorrow all day in that lab?
No. That will actually occur on next Tuesday.
Oh, it's Tuesday.
Tomorrow at 8 is when we're going to do the math, figure out what we should be making. Okay?
Make a big pot of coffee tomorrow.
I'm going to tote it around outside, march around, some chants and stuff.
Also, this was like done in whatever resin ends up being in all of it. Why are some surfaces different than others?
Oh, some of those surfaces were polished in advance of us processing it, and some of the surfaces are roughed out and left that way on purpose.
Okay.
So they get more of what's called bite. It's mechanical adhesion. You would very often bead in here. You try to cement the barrel in one position, but leave it free floating in another, and that's part of how you just make an accurate rifle.
Okay.
So when you have these types of coatings, do you need a type of rheology modifier?
Sometimes you do. Yeah. In those, like if we sell them in 100% solids, usually what you do is you thin to the viscosity for applications. You don't worry about rheology modifier.
Yeah, that's what I was.
But when you have water-based systems, almost all water-based systems tend to have water viscosity in the beginning.
How often do you use this water base?
These are very often not.
Yeah, that's what I was. Because I knew like for water based latex, you get all kinds of all that stuff.